And this is Professor Yoshikazu Takahashi, professor at Kyoto University. He will be talking about, he will give an overview of use of isolation and energy dissipation systems in bridges in Japan. Please.
Thank you very much, and for your so kind introductions. And so I'm Yoshi Takahashi, and so Kyoto University, Japan. So today I'd like to show you that so Japanese situations about that the use of isolation and the energy dissipation devices for bridges. So this slide shows the today's topic. And at first, the presenters in the first session has already mentioned about the function of bearings. But I'd like to remind you again that so function of a bearing for bridges compared with a building. And also, so because that this topic is a very important information for my last topic, that confronting inconvenient truth. So let's start with that the function of a bridge bearings. And due to the big load or that the thermal deformations, and so girders and the deforms, and the rotation and the horizontal movement occurred at the support positions. So in order to release that so stresses of a bridge girder, and we need the bridge bearing, even in conventional bridges. And for isolated bridges, of course, the seismic isolators have to have the basic conventional bridge bearings. And as additional functions, and we need the damping and the isolations for those devices. So in case of buildings, and of course that the conventional building doesn't have that bearings, and the isolated building has also seismic isolators, and so those isolators functions for severe and the seismic event are almost the same as that bridge one, but for the service actions in the daily life, and that they are a little bit different. And the vertical support only is as a primary function for so seismic isolators and for the buildings. So it means that the bridge and how to realize that many and the combination of functions. And so because of those differences, and the international standards have also different specifications for the bridges and the buildings. And of course, the bridges have to have also conventional basic function for bridge rubber bearing, of course. And then that as a result, that the thickness and the also rubber layer are completely different between the bridge and the building. And the second, and scale factors are the same between the shape factor are almost same between the bridge and the building, but so due to the rotational deformations, and sometimes that so thickness of bridge bearing and over one layers, and is so 4 times thicker than that building type. And also that to prevent that excessive and the deformation at the expansion joint, so in the bridge and the bearing use that a little bit stiffer and rubbers and compared with that building type. So and then let's move on the history of a bridge seismic isolation in Japan. So based on the development of the red rubber bearing in New Zealand, and so Japanese and research on the bridge seismic isolation has started. And Professor Kawashima, TI Tech, and his professional career started as researchers in PWRI, MOC, and he strongly promoted that the seismic isolation researches and implementations in the Ministry of Constructions since the mid-1980s. And as an academic side, and Professor Iemura at the Kyoto University, who was my supervisor, and he also started the research on the seismic isolation at the same time. And as those researches, that the first attempt to develop the methodology of seismic isolation was realized in 1989 in the form of a guideline and for seismic isolation of highway bridges. And a more comprehensive manual was compiled in 1992. And so at first, I'd like to show you that the characteristic of base isolation bridges are a little bit different from that the United States or the other countries. And concerning the Japanese situations of a construction site of highway bridges, and the main purpose of a seismic isolation is not that elongation of a natural period. And the main purpose is the improvement of a damping and the distribution of seismic forces into the several piers. So therefore, that the Professor Kawashima and proposed that the Japanese concept to call as a menshin design. Menshin is a Japanese word for the base isolations, but to distinguish that's a typical base isolations and concept. And so, in the Ministry of Constructions, and they started their pilot construction program of menshin bridges and around the 1990s. And this is the first and the base isolation bridges. Miyagawa Bridge was completed 1991, and the lead rubber bearing was used. And the next year, and the high damping rubber bearing and was used in the Yamaage Bridge. And so this bridge and the bearing, and 10 years after the completion, and the original and the bearing was replaced to check that the durability and so performance of the isolation bearing. And based on that some experimental tests, and we could confirm that so original and the performance remained even in that after 10 years. And so 1995, 30 years ago, and the Kobe earthquake attack in the urban area in Japan. And so many steel bearing and the bridge bearing was extensive damaged. And so as the lessons learned from the Kobe earthquake and the menshin design and the seismic isolations design has become a standard for the multi-span continuous bridges. And for the existing bridges, especially for the simply supported bridges, and to enhance not only the seismic performance, but also the drivability or the reduction of traffic vibrations or the maintenanceability. So, and the seismic isolator was used in the retrofit program. And because that the seismic isolators can eliminate the number of expansion joints. As a result of a menshin design, and so super multi-span continuous bridge over that 1 kilometer was realized. And also that the size of the bearing becomes larger and larger, and over that 1 meter squares to increase that the energy absorption. And because that and the location of isolation devices in bridges are very, very limited. Okay, they're only on the abutment on the pier. So, and this and the viaduct is 29 span continuous bridges and using that red rubber bearing. But you can see that the natural period is very short and 1.3 to 1.4 seconds. And because that considering the balance between that the horizontal force by temperature changes and by that seismic force. And this is a different another example. And the Tenryugawa bridges is the bridge length is over 1 kilometer, and the red rubber bearing was used and for this and the continuous girders. And the natural period is also very short, and the about 1.5 seconds. And so this is an example for that. And the large and the bridge rubber bearing. And so Hikari Bridge, and they use that so over that and so plan size is and 2 meters by that 1.7 meters, and with so 10 lead plugs, and also that this is that so largest high damping rubber bearing, and at Kobe Airport, and the plan size is about 1.7 square and the meters. And of course, that we didn't conduct that so deformed test of so real size and bearing and such kind of so large and bearing, and we have to make a scaled model and tested it and with and under that slow rate, okay. And so this is a so example about that damper. And in the bridges, that we usually use the damper as a stopper and to reduce that excessive and deformation at the so expansion joint. And so in the metropolitan expressways in the first incorporate and so the viscous dampers around the 1970s. And but in most cases, that in the retrofit program, and was used and for the dampers. And this is that flexible, and this is the truss bridges with flexible piers, and also that this is so in the continuous bridge, okay. And so in many retrofitted program, and so viscous damper was used. And this is the Minami Aso Bridge in the Kumamoto prefectures, also used the viscous dampers and the BLBs, and in 2009. And so therefore that so we have a lot of example using that so seismic isolation and the dampers. And but so and a very important event and occurred in 2011 and the Tohoku earthquake, of course, and the tsunami and the causes that extensive damage to our and the bridge structures, but even that so earthquake and the causes that damage on the bridges. And the main damage type is a settlement of the abutment, and also that so damage of bearing are still and so large numbers in that Tohoku earthquake. And many steel bearing was damaged, and most elastomeric bearing are not damaged, but not a few elastomeric bearing was damaged, including the ruptures and in that so viaduct of the bridges. Okay. And so this is the Tobu viaduct case, and you can see that so complete ruptures of so elastomeric bearing in the transverse directions, and so we can find that so most and damaged that bearing were located at the end of in the so continuous girders. And this is another example, and the Rifu viaduct. And this and viaduct also and suffer damage on that so elastomeric bearing, and the ruptures and so bearing also and concentrated in the area and about that so in the both end of and the continuous bridges. So I tried to collect that damaged elastomeric bearing in Tohoku earthquake as much as possible. And I was very shocked to see that this kind of result. So we have several break and ruptures in the so elastomeric bearing, and sometimes that we can find that the large cracks. And among them, that so Asahi viaduct has so in the red rubber bearing type. And we can find that so large crack and in this and the rubber bearing. And to inspect that and the reason why that those and the large and cracks was occurred, and the ministry constructions tried to cut inside, and they found that so rupture and separation of a red plug was founded, and also that the deformation of a steel plate also founded. So we cannot understand that why those kind of a separation or red plug was occurred. But just only after the 5 years after that so Tohoku earthquake and the Kumamoto earthquake attack in the Kyushu area, and so many and the bridges were affected. And so one of them that Okirihata bridges, and it is at a 5-span carved continuous steel girders. And so we can find that the alignment like this, and because of the rupture of that elastomeric bearing and on the abutment. So, and we can and carefully check that so location and the position of and the ruptures, and someone and we can find that the inside of rubber layers, and sometimes that so between that so steel plate and the rubber layers. So it has, and those are the reason, and our and that is that the position of so fractures has so mixed inside that so rubber and between the rubber and the steel plate. And so, and this is that so Minami-Aso Bridge, as I mentioned, and as a so example of so and the retrofitted program using that viscous dampers. But unfortunately, that and the failures of attachments and at the abutment was failed. So why that those kind of and the so failures, damages to cars, and even in the so those and so bridges was designed using the Japanese seismic code. Okay, and so in recent and earthquake, in the 2023 Noto earthquake, and the ruptures of and the elastomeric bearing was observed again. So how to confront the inconvenient truth and the rupture and the failure of and the seismic devices, okay, and under the seismic event. So this slide shows that so lessons learned from the earthquakes after Tohoku earthquake. In not a few bridges, seismic isolation bearing were damaged, and the failure of isolation bearing is no longer rare, unfortunately. And we had the confidence in Japanese seismic design and the quality control, including that so durability and of the manufacturing of devices, but many vibration modification and the control devices didn't work as expected in design. Why? So we have to solve those kind of so inconvenient truths. Let's start with that so service and the load service actions, okay? Because that some leaking of so lead from that LRB was observed in that Hanshin Express corporations. And those and the red rubber bearing was constructed just after the 1995 Kobe earthquake. But some and leaking of linkage from the top or the side, and it was observed. And then so, and the Hanshin Corporation cut that and those damaged that LLB, and they found that the separations of so lead plug into the small pieces. So this bearing did not affected by that earthquake motions, okay? So, but so, and those separations occurred. So in order to check that so effect of temperature changes and deformations, and we constructed and we conducted that the slow and the small cyclic loading test. And small means that so, and the strain rate of 4.4% and it depends on that so thermal expansions and in the daily. And so, and we apply that 1 cycle per hour, and they're very small and the cyclic loading. And fortunately, and we cannot find, we couldn't find that any separation of a lead plug in that so and so elastomeric bearing under the current design code. And so, and typical actual pressures of so elastomeric bridge bearing is at 6 megapascal, is so smaller than that building type. But anyway, and so no separation of a lead plug was found in that so in the current design code. But when we decrease that the actual pressures from that 6 megapascal to 0.6 megapascal, And so arc shape and the fractures occurred at the upper or lower position of a lead plug. And also that when we made a slightly small volume of a lead plug, and so similar arc-shaped fractures occurred in the lead plugs. And so of course that in the current design and the detail of bearing manufacturing, like capping of a lead plug at the top and the bottom of a lead plug, have already modified in the current design code. But so we still have so many and existing that old type and the elastomeric bearing in the existing in the bridges. And so we tested that in cyclic loading, we conducted cyclic loading tests of these fractures, lead plug and LRB. Unfortunately or fortunately, that so in the energy dissipation characteristics are not so great difference between those two. But anyway, that we have to consider that so in the deteriorations of that so service and the actions and the seismic isolators. And this is that so for the accidental actions and the seismic event. Okay, this is the main purpose for the seismic isolators. But we still have an inconvenient truth in Japan. Okay, so Japan had an e-defense, and that is and one of our world's largest shake tables, 3D shake tables. And then and the bridge and the column test and has conducted and during the 2002 or 2006 to 2010. And among those cases, that so e-defense bridge test use that the isolators, but it used that the small size. It means that 400 millimeter square, and so high damping rubber bearing were used. And in this project, that primarily focus is a behavior of a column, bridge column. And in this experiment, that the maximum shear strain of an isolator was approximately 20%, and the very small, and the shear strains. And it means that we didn't have many examples of behavior of a bridge and the seismic isolated bridges in the real size. And also, to compile that international standard, and so many real size isolation bearing was tested. And but the most dynamic tests of a real size isolation bearing for ISO were for the building. It means that so in the shear and the modulus is smaller than that bridges, and also that they use the very thin and the rubber layers, and also that large and the axial pressures. So it means that we did not have enough example or the real size and the bridge and the isolators, I guess. And also, and last inconvenient truth is very serious for our Japanese. And Japan didn't have large dynamic test facilities like United States or EU and China and Taiwan, even that we are living in that high seismicity area. So therefore, that we started to construct that new facility, e-isolations. And and this is a project team. So I was the PI of this project, and with the Professor Takeuchi and Professor Wada, and also that Professor Kishiki. And so with those architectural engineers, and we try to construct the project team supported by the Taisei Corporations and the Mitsubishi Heavy Industry Machinery Systems. So e-isolation started the service in April 2023, and the specification is not one of the world's largest, but it has a special and high precise the reaction force measurement system under the large vertical force. So this is the concept and to acquire and precise and the reaction force of devices under the large and vertical forces. And we measure that reaction force at the reaction and the beam side, and not use that actuators data and for that moving platen. And this is the pictures of E isolations, and the red actuator is the usual actuators for that moving platen, and but you can find that another and rod, okay, and attached to that and the reaction beam. So and we measure that and the reaction force at that side. And please refer to that detail about that high performance force measurement method for E isolations and in that ESD, okay. And then that and we conducted that and the bridge type and system at the E isolations. And we confirmed that most reaction force was measured by the uniaxial load cell at the measurement links, and without any modifications and numerically, and we can get that very smooth and the real and the reaction hysteresis and in these systems. And so I'd like to compare with that the bridge type and the building type and the real size and the isolators at the E isolations. And so you can see that and the picture are almost the same, but the insides are completely different. And the bridge type use that thick layers, and 4 times thicker than that the bridge type. And as a result, and so hysteresis loop are completely different, even in that natural rubber. Okay, so bridge bearing and the building bearing are entirely different. So it is important to conduct the research from each other and perspective. And we also conducted the bridge viscous damper test with the attachment at the E isolations. And in this December, we are planning to conduct the bridge damper test with attachment on the bridge girder web at the E defense. So finally, I'd like to conclude my presentation that in several bridges in Japan, due to the several events, not only the seismic event, so isolation bearing and damper didn't work as expected. We should share this inconvenient truth to confront this kind of difficulties and promote the dynamic test of a full-size seismic isolation devices for bridges. So finally, and the vibration control device are the key element anyway. So in order to check the performance for accidental actions, so at the same time, we have to consider that daily actions deterioration too. So thank you very much for your kind.